Hello? Does it work? Okay. My name is Isabella Stilkerich, and I will give a talk about architecture dependable embedded systems. My colleagues, Felix Bräuning and Ulrich Becker from Method Park, supported me in this talk. I will dive into the topics that are relevant for our company. And I'm currently working for Schaeffler Technologies in the field of software development for electronic control units. And the topics that are particularly interesting for us, I would like to focus on today are systems and software development, architectural goals, dependability and functional safety as selected architectural goals, and also real-time and concurrency. First of all, I'd like to give a short insight into systems and software development of my company, Schaeffler. We have a wide range of embedded systems that are contained in our products. So we have, for example, various e-motors, electric motors that we offer at the market, and also products such as the active roll stabilization for cars. And if you have a closer look into these products, you see that they use an embedded system for the control of their respective motor. And on a very coarse-grained view, the e-motor control works in a way that you have some kind of winding, and you have some kind of windings in the system which are attached to transistors, and these transistors have to be switched in a coordinated way, and this generates a rotating electromagnetic field that actually drives the motor. And this correct switching of the transistors in correct time slots is done by the software. The electric control itself, the software for this also supports other functional features that are interesting for us. We have to support several motor types, such as permanent magnet synchronous motors or asynchronous induction motors. There are also various algorithms for electric current controls that have to be implemented. And we also have to provide features such as derating and diagnostics in case, for example, the motor gets too hot, and so that it is not gets corrupt and gets worn out and affects also the life of the people that are sitting in the car. Also, several sensors and observers are attached to the system. But besides all these functionalities that are very important for us, we also have to take into account other architectural goals which are related to software quality attributes. You might know them from the standard, which is called the ISO 25010. And I've shown here a selected set of qualities that are interesting for us. So this is an excerpt from that. So we are interested in functional correctness, for example, the torque precision, the dynamics, and also functional safety topics. Also, performance efficiency is relevant for us. We have time behavior that we are interested in, so that the running of the motor actually works. And also resource utilization and energy becomes more relevant in our situation. Also, availability is a topic which is both good for user experience and also for functional safety. And also security and portability and maintainability are important for us, so that we have a long-term support for our product and our various customers here. And as you might know, it's the case that these qualities are often cross-cutting concerns in an architecture, which basically means that you cannot provide individual architecture modules that fulfill the respective goals. But this is a topic for which concepts have to be developed in a software and also a system architecture. In our situation, for these automotive projects, we have also technical constraints. Most of these systems use AUTOSAR, which is the Automotive Open System Architecture, which is basically a software standard. It's an architectural style, it's a framework, and it also offers implementations for various infrastructure topics, such as operating systems, drivers, and communication systems. And the question is now how to address all these complex topics, the functionalities and all the important qualities that have to be taken into account. And for this, I would like to point out two design principles of architecture that you hopefully have heard of, such as the ones that are listed here: conceptual integrity, loose coupling, and so on. I do not want to go into detail of them. But in this talk, I'm especially interested in the topic separation of concerns and abstraction. And for this topics, it's important for us to have a first look at functional architectures. So functional architectures are a specific architectural view do not concentrate on technical realization in the first place. If we take in cruise control, for example, a functional important building block is that, for example, the current speed is determined. It's not doesn't actually is interesting at this point in time. How does this actually acquire this information? Or that the desired speed is determined. And what is the intention of modeling a functional architecture? So a functional architecture actually lives longer than the technical realization, you could say. So the products that are developed also in our country, in our company, live for decades, and the technical realizations may change due to changes in the technologies and also due to what the customer actually wants at this point in time. And this abstraction, functional architecture, basically represents knowledge about the core function logic and captures the central concepts of the function itself that have to be provided, and also gives a clear overview over the attributes and relationships between those functions. It also enables a better understanding of the function logic for all stakeholders. So also people that take part in the development, besides developers, requirements engineers, and also project managers, and also the customer understand the architecture in a better way. It also helps to find inconsistencies and redundancies in the function itself, and is closely related to domain models that you might know from requirements engineering. Functional architecture is basically abstract from the technical realizations and have an independent life cycle. So typically the life cycle of a functional architecture is longer than the one of the technical realization. The modeling of such functional architectures include structure and also behavior. And you can model functional architecture the same way as you would do for technical architecture. The experts for functional architectures are often not software developers, but experts for the respective field, for example, for electric motors, or for example, physicists. The functional architecture then helps to go into more detail. So what is the realization of the respective functionality? Is it realized by a compound of software and CPU? Do we use an FPGA? What kind of CPU are we actually using? How are messages transported? Is it done via CAN, Ethernet, or FlexRay, for instance? And these are actually technical decisions that then are taken afterwards. Here's an example for technical architecture, a first sketch of this. So it could be for cruise control, technical decision that we use a wheel sensor of a specific type from a company, and that we implement an embedded system for realizing the algorithm, for instance. And of course, these technical architecture have to be refined one after the other to get closer to the actual implementation and to the physical architecture. So in general, you start with the functional architecture and refine this to the technical architecture via specification and respective analyses that have to be performed. And from the system architecture, also the software architecture is realized, and also the other way round. So this is a combination of top-down and bottom-up analysis. The integration itself supports also the evaluation of the technical decisions that have been made also on various levels during architecture evaluation or verification steps such as code analyses or tests that have been executed. So the model itself, the respective views, architectural views are enriched so that we can find out if the solution is the proper one, and one after the other, the solution gets closer to the actual implementation. And this is done in an iterative incremental manner. Now I come to the selected topics, dependability and functional safety, out of the ones that I have shown you before. And afterwards, I will talk about real-time and concurrency as selected topics. It doesn't mean that the other ones are not important, but these are the ones that I selected for this presentation. So if we have a look at these architectural goals, functionality, functional safety, and real-time behavior, we have to see that we have to align these design goals. So these are topics that do not stand for each other alone. But for example, it's the case that functionality often benefits from methods applied in the context of safety relevant systems. For example, isolation is a good property for applying methods for availability, and also real-time properties are good for a good user experience, overall good user experience. The safety mechanism themselves should not be just mounted on top of functionality. So everything is equally important and should be taken into account in the analysis right from the start. These topics are cross-cutting system aspects, as I mentioned before, and they have also to be respected at all these levels, at the system level, and in our case, also the hardware and software levels, and in some situation, also in the other areas, such as the mechanic level, for example, for such an active role stabilization. These disciplines rely on each other, on the analysis they perform, and they have to have a close communication with each other. So this procedure of creating such a complex system actually works. And the properties themselves should be handled as any other functionality in there. So you cannot say that, for example, a functionality is more important than, for example, some safety features that have to be taken into account. And with respect to safety, there's also a standard in the automotive industry, which is the ISO 26262. And this is a pretty vast standard. And it has to be followed for getting releases for cars before they go to market. And they have one topic in the standard, which is called freedom from interference, which basically means that software elements should not affect each other in unintended and negative ways. So if you have applications in your system, they should not affect each other in a negative way, so that, for example, one application corrupts data of another application, and also not the data of infrastructure services such as the operating system and so on. And in the standard, they also tell you what you could do to achieve freedom from interference. For example, they point out that regarding timing and execution, there's temporal isolation via monitoring mechanisms, as execution, budget analyses, and also scheduling mechanisms. They also give some hints what you could do to make sure that memory accesses are not corrupted by performing mechanisms for spatial isolation, such as semantic code analysis or using a memory protection unit, for instance, and also having a safe exchange of information and so on. So, and if you have a look at all these regularities, they are basically hints for you, but they are also, of course, important for the functionality itself. So the freedom from interference is not something that is just in the standard, but it's, of course, necessary so that the application actually works. So in the automotive industry, it was for a long time the case that the software instances were physically isolated with each other. So you have various electronic control unit, these ECUs, with the CPUs on them in the car network. And the individual functionalities were pretty small and isolated from each other. But having all these devices in the car is also costly. It consumes space in the car, and it also, all these devices have to be interconnected with each other. And this cabling is also pretty expensive, and it's pretty heavy. For example, there are over 50 kilograms of copper in a car for cabling, and they would like to reduce it. So they have the need, not only for safety reasons, but also for other reasons, to reduce this set of interconnections here. And the idea is to go more for an integrated architecture, so that you have some kind of computer in your system, a more powerful computer that executes the functionalities, and that you might have maybe smart sensors in the system, but you do not have to have so much cabling anymore that could get broken afterwards. But of course, moving from such a federated architecture to an integrated architecture also comes with new problems here. They are not physically isolated from each other. So you have to provide, for example, means to separate these software parts from each other in software, for instance. So in this topic, isolation is also has a close interconnection with the timing topic. And that's the reason why I switched into this topic. And we will also see how this has backward relation to the isolation topic again. So regarding real-time systems, there's also a standard, which is the DIN 44300, and this is the standard for information processing. And what does it say about real-time systems? So the statement is real-time operation is the operation of a computer system whose programs for data processing operation in a way so that processing results are available in a specified time span. So that's what's interesting for them. So you have the specification at hand from the top-down design. You say at which point in times results should be available. And this is actually also carried out by the implementation. And depending on the use case, as they say here, the data can also be delivered with a random temporal distribution or determined points in time, as long as they arrive before the specified time span. So that's actually depending on how your system then makes the implementation for that. And during the design of such a real-time system, you have to think about results and also what are events in your system. So is there an event that there is some kind of accident and the airbag has to inflate? Or is the event that there is a new positioning information coming into the system for your navigation system, for instance? And this event has to be processed. Some kind of algorithm has to be carried out in reaction to that to provide the functionality to the user of the system. At the point in time at which this information has to be available is called a deadline. So, and what some people think is, okay, timeliness has to do something with fastness. Fastness is good, of course, but it's not a guarantee for real-time capability. So you might have a very powerful machine, a powerful processor, but you might have asynchronous interruptions in your program, and that may affect your program execution, for example, in an unpredicted way. Another problem is also that time is not an intrinsic characteristic of the computer system itself. So there's the physical time, and of course, the instance in the computer that actually is important for giving the programs the information which time it actually is. And this computer system's time scale may not be identical to the one of its physical environment. And for this reason, you have to reason about what are the relationships between them. So how do I map physical time to the computer systems time in a sense? And for this, you also have to take into account various levels here, starting from the system level. So you have to know your product. You have to know what the functional architecture is. We have to know at which point in time specific values have to be calculated. And then we have to think about how our computer system actually does that. What kind of software elements do take part in realizing the algorithm? Is there the application itself? Is there a runtime system below that, an operating system that schedules the execution of different portions of code? And of course, what kind of processor is actually employed? And this has to be examined. And for this, it also helps to differentiate between those two words, the function and also the technical architecture afterwards. Timely execution is a very complex topic. So it's something that you cannot just have one analysis for. So this affects various topics at the system architecture level, at the software architecture verification, and also reasoning about the system at runtime. So we have to think about the determination of logical worst case execution time at the functional architectural level and decompose it to the technical architecture and think of how the execution budgets could be here. We have to reason about what kind of CPU are we actually using? Are we in a distributed system, or is the application deployed monolithically on one electronic control unit? What is the task architecture of our system? What is the application? Are there dependencies between modules that have to be taken into account? Then we also have to verify those specifications. So we have to define in the architecture what are the specific time spans that have to be followed, and then the implementation itself has to follow these ways. And if this is not the case, we have to think about where the actually problem comes from. Is it a problem of the software architecture? Is this a problem that might arise because the CPU might not be that powerful enough? And so on. As you see, there are lots of mechanisms that are important here, and software itself cannot solve the problem. So what might be interesting here for the software side is the creation of so-called thread or task architecture that I would like to go into detail now. I also asked and answered the question, so is temporal and spatial isolation a software topic only? So actually, it's not. We have to have our constraints at hand from the system level. And also we have to think about CPU time and memory, which must be shared across the components. And this sharing is actually implemented by an operating system, specifically the so-called scheduler of the operating system. And in real-time operating systems, such as scheduler, provides some kind of framework for the construction of a real-time system. So which basically means just using an operating system like this doesn't help me alone doesn't help me to achieve the real-time capabilities, but I have to use the operating system in a way that it is actually able to provide an execution for me that fits to these real-time requirements. As a software architect, I have to reason about my thread architecture or task architecture. I use thread and task as synonyms here, so don't be confused by this. So in embedded systems, we talk a lot about tasks. In other systems, you might call this basically a thread. So, and on the other side, you also have to think about where the thread actually is executed. So this is something the runtime system will not do for me, as it might be in other systems where actually efficiency is not, or the limitation of resources is not that important. So, and these scheduling and isolation topics are not only software topics. Of course, there's the schedule itself, so the specific part of the operating system, a software part. But I have to tell this software implementation how I would like to execute my code. And for this, I have to perform the analysis pretty early in the during the system creation. So I have to think about mathematical scheduling analysis on the functional and technical architecture level. For example, executing methods such as rate monotonic analysis. And I have to select the CPU. I have to think about a distributed system design. And I also have to take into account that these topics influence each other. So just to give one example, if I decide also for a functional safety system that it might be beneficial to have redundant execution of my code because computation could be corrupted by a hardware fault or by a faulty algorithm, for example. Might be good for functional safety topics, but it might also affect timing topics in an unfortunate way because it takes so much time to compute, or if you have any other kinds of faults in the quality areas that I discussed before. And all these interconnections have to be thought of during this holistic analysis that are performed at the system, software, and hardware architectural level. Coming back to scheduling, we have the topic also at the implementation level. So after we decided on the functional level, by using these mathematical methods, we have to implement this in the operating system. So the operating system scheduler has to be fed with the information about how important is in a certain part of the program, because it doesn't know it itself. That's the application architect actually knows that. So as an architectural, I have to assign priorities and also tell the operating system something about dependencies in my program. And with my analysis that I performed on the architectural level, I can then give the information to the operating system, and then the operating system can create a schedule which follows these constraints that I have given as an architect of this system. So you see, this is a software architectural topic and also a topic of the operating system. So I have to know also what the operating system does, so that I can be sure that it fulfills my requirements in a way. Regarding the topic separation of concerns, it's also the case at the implementation level of scheduling, that you have on the one hand side the planning strategy of the operating system. There are also different mechanisms. There are time-based strategies, then there are priority-based strategies, and so on. And that's what I also have to be aware of as an architect. I have to see how this works, and I have to select a strategy for this. So I must be aware of these patterns that are implemented here in the operating system. And dispatching itself, so actually saying that this thread is currently executed, this is something that is then implemented by the operating system according to the strategy and the thread architecture that I predefined as an architect. The overhead of this task management setup depends actually on the type of the task or the thread. So is it a process with a separate address space? Is it something that is separated from the operating system, the kernel? Or is it something only the kernel sees, no address spaces at all? And also the management costs that are associated with this. And the scheduler basically works with so-called threads of control. And this is also an abstraction of the operating system that is provided to the programs from the application layer and also to other infrastructure software programs, for example, drivers or communication services, for instance. And this is, a thread is, you could say, a software modeling element such as any other software component. So what you do in an embedded system is that you think of a so-called thread architecture view, which you define as an architect. So you think about which kind of threads do I have in my system? What are the relations between those threads? How do they relate to software components? Are 2 or 3 threads executing my software component, or are 2 software components assigned to my thread in the system? What are the interconnections between the threads? Are there dependabilities that I have to take into account? And also the assignment of these properties to the task. So how important are they Can they interrupt each other? Can they preempt each other? What kinds of events do activate these threats? And also, what are the isolation zones? What are the address bases of the threats is something also that I have to take care about in an embedded system environment. The threat, this approach basically of having a separate module, the operating system for the threat management is basically following the separation of concerns principle again. So you separate what, which means the code, from how this is actually executed. So you can say that the OS actually encapsulates the architecture goal timing behavior somehow, to some extent, in the software architecture, and together with the threat architecture that is developed by the architect, you can develop a concept that is clear, that that can be used to evaluate if the timing requirements are fulfilled. Having also a separate module for scheduling here supports also reusability and extensibility, in contrast to just having one thread in your system, because otherwise you would have to think as an application architecture of how you would have to cut down your program into pieces so that it is executed by the CPU. So, and there are also patterns for doing this in the past where people didn't use operating system. There were single-threaded patterns such as the cyclic executive pattern, which seem pretty straightforward in the first place. But when you try to extend them, having lots of complexity in your code, you will see that this actually doesn't scale anymore. And the threat management itself, of course, depends again on the thread architecture. You have the single-threaded program in contrast to the multi-threaded program, and on these various kinds of isolation constellation, of course, cost. And this multi-threading itself, you could say, leads to new architectural issues that need to be solved. For example, you have to verify that your scheduling decisions are correct also at the implementation level. And you have to design the address spaces, so the memory protection zones, and also the handling of concurrency situation in case multiple threads work, for example, on the same memory location, also have to be taken into account. So just to give an example, this is an example from a mapping scenario in AutoSAQB. So this is the operating system of this architectural style, which we are basically using. And as an application architect, I would have to decide on which cores in a multi-core system my application basically runs. I have to think about which kind of threads or which kind of tasks do I have in my system. Which kind of data can be accessed from these various tasks here, and are they isolated from each other? So I have to reason about control flow isolation and application isolation, and also if also parts of the program might also be trusted. So because it might also be an architectural decision to say, okay, this is some code that has to run with privileges, and it is so small that I can verify it in a way so that I give special privileges to this so it can run in the context of the operating system. Might also be the case. But this is something I have to account for as an architect in such systems. I also have to think about the overhead of thread management. Here's just an example for Unicore system. So just one core 0. And I have to think about, well, do I have just a single thread? It's just a function invocation. I have to think about my activation record. How large is it? Activation record basically means pushing, for example, the parameters to stack and then coming back from the function invocation. And in case of multiple threads, if I have a single address space, I have to take into account the thread switch times, plus the overhead of function invocation and the update of registers. Or if I have separate address spaces, multiple isolation zones, I have to have the system call overhead in mind, and also the overhead of handling a single address space plus the trap handling. And for multiple isolated address spaces, I also have to take into account, besides the other things, also the update times for the memory management unit and or memory protection caches in this sense. And this is something that has to be taken into account during timing analysis. And therefore, I have to have an insight into the architecture of the operating system and how it actually does that. Also, concurrency issues might be a problem. Here's also a problem that is sketched. So we have this lost update problem often in situations where we have multiple tasks, multiple threads. So here's an example where two runnables are mapped to separate tasks. And a runnable, you can think of a runnable, which is determined from AUTOSAR as some kind of function, a method, which is mapped to one task, and a function that is mapped to another task. And this just updates a memory location. Here you see there's the memory location X. And then this memory location contains the value 3, and 5 should be added to this. And afterwards, 8 should occur after that. So on both functions should do that. And if we have multi-threading now in mind, and the scheduler can interrupt me at any time, then these instructions that are carried out to update the memory cell are not, this cannot be seen as an atomic situation that might occur. So I can be interrupted within or during reading a value, and another task could run. For instance, here in this situation, the function that is mapped to task 1 can be preempted by the function after it read the value 3. Then the other thread 2 resumes, again reads the memory cell 3 and adds 5, coming to 8, and then the scheduler decides that the task 1 can run again. But the memory cell hasn't been updated for the thread. So it still has, in this situation, in its local cache, the value 3. So, and afterwards it writes 8 back to the cache, to the memory location afterwards. So it should be 13. So an update situation, an event basically was lost in this situation. And of course, there are patterns to solve such problems, and I have to be aware of these situations in an embedded system. So I could use, for instance, the priority ceiling protocols, spin locks, suppression of interrupts, or have some kind of systematic scheduling in mind so that these overlapping situations do not occur in all, or that I perform my mapping in a different way. And these topics are pretty vast, and I hope I gave you a small insight into the complexity of the design of dependable embedded systems. And if you are interested in more information about that, if you're working in the domain, you're invited to our Dependable Embedded Systems course. And these topics that I talked about today in this presentation are also part of this curriculum of the iSAQB, Certified Professional for Software Architecture Training. Thanks.